So we have got on to looking at ways of ascertaining deflection in reinforced concrete beams, and that's what lecture number 12 deals with today. Deflection in the code falls under the heading of serviceability, and so it is probably the most important item under serviceability. But if you have a look at AS 3600, you'll be able to read up on serviceability, and I'd strongly suggest you do that. We're going to look at a formula by a fellow called Branson, who came up with this formula in 1975. It's since there's a possibility that it will be replaced by somebody else's formula, a fellow called Bischoff. But at this stage, we're looking at Branson's formula. And what we want to do is see how much this beam actually deflects in the center. In other words, how much it sags. That dimension there, as you all know by now, is the deflection. So it can deflect under its own weight, and it can deflect, obviously, when you put live load and additional dead loads on top of it. Many laboratory tests have shown that the cracking near the center of the section, where the deflection is the greatest, is greater than the deflections greater than the cracks as you approach the supports, and that's why this drawing illustrates that. Now, Branson's formula is this: the effective IEF equals the inertia cracked plus the inertia gross minus the inertia cracked multiplied by the cracked moment multiplied by the moment where you have not factored up the loads, all cubed. But you'll see once we get into this how we operate with that. Now, the cracked moment of inertia is given to you by this formula: I cracked BD cubed over 12. It's the breadth of the section multiplied by the depth of the effective depth of the section cubed over 12. And you recognize that from your studies in Struct 1 and Struct 2, but it's the effective depth, not the overall depth. We do deal with that later. Multiplied by 4 times K, and K is a factor generated by the root of the modular ratio and the steel ratio, because that's N is the modular ratio, P is the steel ratio, which you're quite familiar with in looking up areas of steel in your graph and so forth. And that's how you compute K, which plays an important part in this formula. And N, as I was just saying, is the modulus of elasticity for the steel divided by the modulus of elasticity for the concrete. And if you do that absolutely correctly, you end up using this formula: 0.043 times mass multiplied by the root of the concrete strength. But what I'd strongly suggest is you take this shortcut, which varies slightly, gives you the elastic modulus for the concrete, merely 5,000 times the root of the concrete cylinder strength. That's the one I would use, and I use. And then the cracking moment is given to you by 0.6 from the code, the root of the concrete cylinder crushing strength by the gross inertia divided by the distance from the center of the beam to the outer fiber. And for long-term deflections, we have this formula here, but the example I'm going to do will actually illustrate these things. So let's move on. Example: the reinforced concrete beam shown below supports a total uniformly distributed load, including its own weight, of 10 kilonewtons per meter. The load is unfactored, with approximately half being dead loads and the other half being live loads, G and Q. Determine suitable reinforcement for the positive moment region. And so you'd be looking at the biggest moment, which would be WL squared over 8. And with the calculated reinforcement found, determine the long-term mid-span deflection using Branson's equation that we've been talking about. And there the beam is 12 meter span, live load 5 kilonewtons per meter, dead load 5, total 10. These are the given factors. This is a cross section through the beam. It's got some steel in the top, but those would just be tie bars. So we're interested in working out what the main tension steel is in the bottom of the beam. Got an effective depth of 550 and a breadth of 350. Now, this solution here is a bit, from here down, is a bit long-winded. I mean, it is the exact solution as computed using the code formulae and the stuff that you actually looked at and learnt about in your first lecture, or lecture number 8. So you can go through this and you'll end up with a quadratic equation, and you solve the quadratic equation and substitute that, you'll find the area of steel. You'll find that you need 0.001156 cubic meters of steel. So that's a cube there, cubic meters of steel. Sorry, that's millimeters squared. Millimeters squared, that's correct. Millimeters squared, yep. Meters squared, rather. And when we look at our tables, we could select 4 N20 bars, 1256 millimeters squared. But what I want to run past you is just using the system we've been using to date in my lectures, using the graph. The moment is 243 kilonewton meters. Now, there it is. 1.2 times your dead load, which is 5 kilonewtons per meter. It was given to you. Your live load, 1.5 times the same load, because the two loads were equal, gives you 13.5 kilonewtons per meter. 13.5 kilonewtons per meter. And our moment then is WL squared over 8. So putting the load into this formula, we've got 13.5 kilonewtons multiplied by the span squared over 8 gives you a moment of 243 kilonewton meters. And that's fine. Do that. But I'd suggest that you shortcut all this by doing what I've done here. Your moment is 243 kilonewton meters. You know that lambda is m over bd squared, the ultimate moment. This is the ultimate moment because it's got the factored loads. Over bd squared gives you a lambda of 2.295. If you look along the bottom axis of your graph at 2.295, go up to the 32 FC concrete strength, then P equals 0.006 from the graph. So the area of steel, as you well know by now, is PBD. P times the breadth of the beam times the effective depth. P times B times D. 1155 square millimeters. Now, we just did a graph. We did a few lines of calculation. And what I want to just reinforce here is that this is going through the code, working it out exactly, working out the area of steel exactly, doing quite a bit of mathematics, and we came up with 1156 square millimeters of steel. And I got 1155 using the graph, 1 square millimeter of steel difference. So it's really easier to do this if you have this sort of problem, if you have to compute the steel. But be accurate in your assumptions. So with that steel, we can use the 4N20s as we have in this particular problem, because by doing the thing the simple way, we also got 4N20s, 1256 square millimeters of steel. So now we get into using Branson's formula. And right, so start off by working out your elastic modulus. As I said earlier, this is the formula I'd use, and you find that your elastic modulus using 40 MPa concrete is 34,500 newtons per square millimeter, or MPa. The modular ratio, as you well know from Struct 1, when you're doing a concrete section, is the E for the steel divided by the E for the concrete. And that's what we've done there. The E for the steel is 200,000 newtons per square millimeter divided by the E for the concrete, which we've just computed there, gives us a modular ratio of 5.8, and that is what N's value is. The steel ratio is 0.00652. I did that graphically, and it's been done the long way around on the previous page. But P is merely the area of steel divided by the breadth times the effective depth. And K, a factor that you have to calculate to use to ultimately work out Branson's formula, is the root of the modular ratio multiplied by the steel P, the steel ratio, all squared. This formula, the N's and the P's are certainly self-evident. There the N is and there the P is. Substitute those in there, those numbers, and you get a K value of 0.241. This is Branson's formula. We've got I gross that we haven't worked out yet, and I gross is BD cubed over 12. I've done this in meters to simplify the size of the calculation. So we've got a breadth of 350 mil, or 0.35 meters, multiplied by an overall depth of beam. If you look back a few pages of the sketch, you'll see it's 600 deep, so it's 0.6 cubed. BD cubed, overall depth, not effective depth, over 12, gives you a gross moment of inertia of 0.0063 meters to the fourth. We now look at the cracked moment, which is the gross inertia, which we've computed there, divided by YB. And YB is merely the distance from the center of the beam to the outer fibers. You're familiar with that statement by now, I'm sure. From the center of the beam, this beam 600 deep. So from the center of the beam to the outer fiber, top or bottom, is 300 millimeters. And that's where the 0.3 of a meter comes from. So substituting the knowns into this so that we can work out the cracked moment, the moment that actually cracks the beam, we've got 0.0063 meters to the fourth divided by the distance from the center of the beam to the outside fiber, 300 mil, or 0.3 of a meter, multiplied by 0.6, which is a given factor, multiplied by the root of the concrete cylinder crushing strength, and that gives us a figure of 0.0796 meganewton meters for the moment. Move the decimal point 3 places to get into kilonewton meters, and you end up with a cracked moment of 79.6 kilonewton meters. You can do it the long way if you wish. If you want to use millimeters throughout, you can. But this works very well when you're working with MPa. You can work with meters and you don't have a problem. Now the actual moment using unfactored loads, and you'll remember when we do deflections, as we did in structural steel actually, when we're looking at deflections, we don't use the factored loads. So the actual bending moment using unfactored loads, MS, WL squared over 8. Remember the live load was 5 and the dead load was 5. That gives you the 10 kilonewtons. WL squared over 8, 180 kilonewton meters is the unfactored bending moment. And that we'll be using in Branson's formula presently. Now, the cracked inertia, BD cubed over 12, multiplied by these factors which we've computed on previous pages. That is the formula for the cracked inertia. There your breadth of your beam and your effective depth are, BD cubed over 12. We use effective depth there, not the overall depth. These are purely substitutions from the work that we've done prior to this in earlier pages, and we get an I cracked of 0.00156 meters to the fourth. Remember, inertia is always to the fourth power. Now, substituting all of the above, the stuff we've done in Branson's formula, we get the I cracked 0.00156, and just looking back at Branson's formula, here we have it. We've got the gross inertia there, 0.0063, minus the cracked inertia, okay? Quite a big difference between the gross inertia and the cracked inertia. The cracks actually reduce it considerably, as you can see. Multiplied by the cracked moment divided by the actual moment using unfactored loads, which we had up at the top of this page there, 180 kilonewton meters. All of that cubed gives us an effective inertia through that computation of 0.00197. We now substitute it in a formula that you are probably all aware of, the 5WL to the fourth over 384 EI, but it's been modified by these factors that we've used to actually do Branson's. So delta, the deflection, is 5WL to the fourth over 384, E for the concrete, times the effective inertia, 0.00197. Substitute the knowns into this. We've got 5, which is a standard. 0.010 is the load per lineal meter. We worked that out in kilonewtons, meganewtons, and times 12 to the fourth, divided by the standard 384 times E for concrete, which we computed right early in the piece, multiplied by the effective, the I effective from Branson's formula, gives us 0.0403 meters. And if you divide that through by 1,000, the actual deflection is 40.3 millimeters. Okay, or you multiply by 1,000, sorry. The actual deflection is 40.3 millimeters. The deflection limit on beams like this is usually the span, the length of the beam divided by 250. Our span of beam is 12 meters, or 12,000 millimeters. And if we divide that by 250, it gives us a figure of 48 mil. So the code says we cannot have a bigger deflection than 48 millimeters. But in fact, our deflection worked out at 40.3 millimeters. So our steel, our loading, everything is okay. So therefore, the calculated actual deflection is permissible. That's nearly 8 millimeters less than what you're allowed to go up to. Right, thank you. Right, so I've included this exercise here, which I will be doing in the tutorial. So I'll just put that aside for a moment. This is the problem we're going to do in the tutorial. I've reproduced it on the tutorial sheets. There's another method of working out deflection, and it's called deem to comply. It's an easier procedure. It gives very conservative solutions. In our course, we don't really have time to go through it and practice it in any detail, but for students who are interested in looking at this deem to comply method, you'll see that something in Branson's that took us 3 or 4 pages, you do in 2 pages, like this. This graph is found in concrete textbooks, reinforced concrete textbooks. Here it is. It gives you this minor variations and adjustments for the type of loading and so forth. Pretty straightforward. Deem to comply. but I'm not going to do that, but I have just included this for your interest's sake. This is a list of the symbols that we've used, taken straight from the Code of Practice. And with that, we end this lecture. Thank you.